Hey everybody, Mr. Piercy here, and what we're going to be looking at is another recap video of an investigation that we did concerning angles of polygons. Particularly, we're looking at the measurements of regular polygons, in this case the interior and the exterior angle measurements. Now remember, a regular polygon is a polygon where all of the sides and all of the interior angles are congruent to each other. And what we're seeing in the pictures that are shown is this. It's hard to read on the screen here, but on your papers maybe it was a little easier. That is your interior angle, and like here where it's pointing at the angle outside of the polygon, that obviously is an exterior angle. Make a note of how the exterior angles are constructed. All of the lines that extend from the polygon all extend in the same direction, creating kind of like that pinwheel shape there. So however I go for one, I'm going to follow that same pattern all the way around the polygon. Now looking here, this is kind of a mental exercise where we're kind of taking what we know about some polygons from a previous investigation, and now we're looking at them as far as a regular polygon, not just this general polygon. Now, filling in the table, we should have seen something that looked like this, where the number of sides are increasing by each time, and we can see that very easily by what the polygon name is. The sum of the interior angles was provided for you in the table, but it is also something that you got from the previous investigation if you had done it. And so that's how we're getting those numbers in that column. Now, the measure of the interior angle. This is where we're breaking off into new territory for this investigation. If all of the angles have to be the same, and I know the sum of the angles, well, I just say whatever the sum is divided by however many sides there are, however many of the angles there are. So that's how we're getting the expression that we see in the middle of that, or in the bottom of that column, n minus 2 times 180 divided by n. So what about the measure of the exterior angles? Well, same idea. The measure of the exterior angle and the interior angle, they're supplementary to each other. So if I know the interior angle, I can get the exterior angle, or vice versa. So that's how we're saying, it's hard. I tried to type it in as best I could. This here, where it says 360 divided by n, that's one thing. And then the other way that I could find the measure of the exterior angle is if I know the sum, or if I know the measure of an interior angle, which is the expression n minus 2 times 180 over n, well, I can simply subtract that from 180, and that would tell me the measurement also. This is also going to be something that we'll use later on. This will also be something polygons. We're not there yet, but that is going to be something that we'll talk about when we get there. That's how we would find the measurement of the central angle of a regular polygon also. Now let's go ahead and start answering the questions here. Based on what you see in the table, what happens to the measure of the interior angles as the number of sides increases? Well, as the sides increase, we can see that the measure of the interior angles are also increasing. We start from 60 to 90 to 108, 120, and so on. So the more sides there are, the bigger the interior angle. Is the relationship of the interior angle and the number of sides linear? Why or why not? Well, in this case, no, it's not. It's a little, you may be able to see it just by looking at the numbers and say, well, it's not increasing at a constant rate. And so what I did is I'm looking at the slope that would be formed between two sets of points when I compare the number of sides and the measure of the angles. And when I compare those, I get a rate of change of 30 one time and a rate of change of 18 the next time. So because it doesn't have a constant rate of change, it absolutely cannot be linear. So what you see on the table, write a conjecture about the sum of the exterior angles of a polygon. Well, the sum of the exterior angles of a polygon, based on what I'm seeing, is that the sum of all of the polygons, doesn't matter how many sides it has, will always be 360 degrees. So here we're going to take a look at our table. So taking the set of data points that we saw in the previous table, we're going to put them in here with the angle measurements, and then we're going to plot the points on the graph. Now make sure you just scale your X and Y axis appropriately for so that you can fit it and see it clearly. I'm counting every other line on the x-axis as one space, and basically on the y-axis going up, every line is 10 degrees. So at 30, or I'm sorry, at 3 sides I have 60 degrees, and at 4 sides 90 degrees, and so on. And this is also going to reiterate the idea that the fact that no, this is not a linear function. There's a definite bend in the set of points that we see here. So as the number of sides increase, the measure of the angle also increases. What's the largest that the interior angle can be? Well, let me look at the graph here a second. And I'm intentionally not drawing in the points here. I'm not drawing in a line on purpose, but if I did, it would kind of follow one of these things, and it would ultimately get up to a point where it just kind of looks like it gets to 180 degrees, but it really doesn't. It would approach 180 degrees, but it doesn't actually get to become 180 degrees. The type of function that we're actually seeing here is not something that you generally get introduced to in Algebra 1, but it will be something you talk about in Algebra 2 and other math classes. This is what we would refer to as a rational function. And what we're seeing here, this is what we would refer to as a horizontal asymptote. So coming back to my question, well, what's the biggest number that the interior angle could be? Well, it has to, if it's equal to 180 degrees, it's a line and it's not an angle anymore. It's just a line. So it has to be something that's less than 180 degrees. So what does that mean? It's 179 or 179.9 or 179.999? We don't know, so we just say it has to be less than 180. Why are there no negative numbers used? Well, that should be fairly obvious. The function itself can use negative numbers, but for our purposes, the negative numbers are going to be excluded because, again, we can't have a polygon with negative sides or negative angles. So we're sticking with positive whole numbers in this case. How could the equation be used to find the sum of the interior angles? Well, we kind of answered that from our table. We take that expression, n minus 2 times 180, and we just divide that by n, the number of sides that there are. And as the measure of an interior angle increases towards 180, what happens to the exterior angle? Well, if the interior angle gets bigger and bigger and bigger, the exterior angle conversely must get smaller and smaller and smaller. Because the two angles are supplementary, they have to have a sum of 180. So as one gets bigger and bigger, the exterior angle must get smaller, so that way the sum of the two is still 180 degrees. So that's pretty much it for our investigation with the angles concerning regular polygons in this case. And these are going to be the last two things that we really talk about as far as just angles of polygons in general. But hopefully you were able to confirm or clarify any of the answers that you wrote down on your investigation. But if you have any questions, obviously, by all means, let me know. And until next time, guys, thanks for watching and take care.